Interpreting a hypothesis test generally comes down to comparing a p-value with a significance level alpha and using that comparison to decide whether to reject or fail to reject the null hypothesis. For example, starting with the sample from the previous section and the null hypothesis that the mean of the population is 1,000, the p-value can be computed using the t-test function. Comparing that p-value with the significance level leads to either rejecting or failing to reject the null hypothesis, and in the real population the null hypothesis is either true or false, which leads to a total of 4 possibilities. 2 of those possibilities are correct and 2 are incorrect. One correct conclusion is rejecting the null hypothesis when the null hypothesis is false. Rejecting the null hypothesis is sometimes called a positive result, and if the null hypothesis actually is false, and so should be rejected, this is called a true positive. The other correct conclusion, called a true negative, is failing to reject the null hypothesis when the null hypothesis is true. If the null hypothesis is true, then there is no real effect to be detected, and so failing to reject the null hypothesis is the correct conclusion. One incorrect conclusion is a false positive, which happens when randomness is mistakenly interpreted as a real effect, or in the terminology of hypothesis testing, a false positive happens when the null hypothesis is rejected even though the null hypothesis is true. A false positive is also called a type 1 error. The other incorrect conclusion is a false negative, which happens when a real effect is missed due to randomness, or equivalently, when the null hypothesis is not rejected even though the null hypothesis is not true. A false negative is also called a type 2 error. The chances of a false positive or a false negative are affected by the level of significance, and so the choice of level of significance depends on whether it is more important to avoid false positives or more important to avoid false negatives. If the null hypothesis is true, the significance level is the probability of a false positive, so in applications where it is important to avoid false positives, the significance level should be small. The probability of a false negative is more complicated since it depends on the level of significance and on the size of the difference between the null hypothesis and the actual population. It is easy to detect a real effect and avoid false negatives, after all, if the real effect is large. Here's a plot of the rates of false positives and false negatives for different values of the significance level in this example, showing a low rate of false positives if the significance level is small, and a low rate of false negatives when the significance level is large. For example, if the mean of the actual population differs from the null hypothesis by 1 standard deviation, which would in many cases be a relatively large difference, then in the example considered here, with sample size n equals 25 and significance level of 5%, the rate of false negatives is about 1 in 400. As already noted, the choice of significance level depends on the application, and in particular on whether it is more important to reduce the rate of false positives or more important to reduce the rate of false negatives.